Hey, Professor. This is Hitesh Chaudhary Adusmali from Group 12. I'm presenting today's literature review along with Vishnuvardhan Reddy Meda. Our literature review is about an experimental study on tuning the consistency of NoSQL systems by Xiaodong Huang, Jie Wang, Philip S., Yu, Jianbai, Jie Zhang. Coming to the introduction slide. What is NoSQL? So discussing about the NoSQL, it stands for not only SQL, a non-relational database which has no tables. And it is also a flexible database which is used to handle big data and also for real-time web applications. There are multiple types of NoSQL databases like document databases, example MongoDB, CouchDB, key value stores like Redis, Couchbase Server, column-oriented databases like Apache Cassandra, graph databases, Neo4j. Each type solves a problem that can't be solved with relational databases. So these are the advantages of NoSQL over DBMS. Looking at the diagram, the central cubicle is the NoSQL database, and the 5 things connected to it are its attributes. So coming to the attributes, NoSQL database is highly scalable, is capable of processing big data. It gives out the fast performance. It is highly available, and also and one of its attribute is easy replication. So discussing each and every attribute in particular: scalability, ability of database to handle the resources; availability, ability to allot resources when requested by consumer; big data capability, large data sets can be handled with NoSQL; easy replication, data can be written in more than one node. This promotes high availability of data. And also there's we have the additional attribute with this, naming consistency in NoSQL. Next slide. Continue. What is consistency in NoSQL? Consistency, a property for databases, where once data is written into database, queries that follow are able to access the data and get a consistent view of the data. In practice, this means once a record is written into database and then immediately request that record, you're granted and guaranteed to see it. It's particularly useful for things like Amazon orders and bank transfers. Ongoing research efforts are made to quantify the consistency in NoSQL systems. Most works focus on consistency, latency, and trade-off. For example, the consistency as logical monotonicity CALM theorem was proposed for guiding developers to design programs under the eventually consistent systems. The term consistency in NoSQL world falls into 2 camps: atomicity, consistency, isolation, and durability, abbreviating to ACID, which means once data is written, you'll have full consistency in reads. And the other one, abbreviating base, which is eventual consistency. That means once data is written, it will eventually appear for reading. Eventual consistency. Many applications can tolerate inconsistency for a long time. Web page updates, web search crawling, indexing, and ranking updates to DNS server are some of them. In such applications, it is acceptable and efficient if replicas in the data store rarely exchange updates. A data store is termed as eventually consistent if all replicas will gradually become consistent in the absence of updates. Typically, updates are propagated infrequently in eventually consistent data stores. Research article. Knowing about this research article, in this research paper, Xiaodong Huang addresses the problems by presenting a systematic study on the client-centric consistency of a popular quorum NoSQL system, Cassandra. The team has analyzed the root cause of consistency anomalies using the right queue and proposed solutions to control the replica consistency under session guarantee consistency model. Next slide. Tuning consistency of NoSQL systems. The eventual consistency model base has been widely adopted in NoSQL systems. By tolerating weak consistency, these systems attain high availability and throughput while sustaining side effects on user experience and developer friendliness. But the widely ignored problem in these systems is how to control the consistency of an existing system without the necessity of modifying the system implementation, without the necessity of modifying the system implementation, as I said earlier. Sorry for that, yeah. That is how developers can achieve a desired consistency degree by merely tuning the configuration parameters according to hardware specification. Oh, give me a minute. And yeah, we're moving to the analysis of consistency anomalies. First, the analysis of read-write process, and then summarize why consistency anomalies occur. After going through extensive experiments, it is observed that consistency is closely related to the length of the write queue and can be substantially enhanced by tuning the system configurations. Second, empirically evaluate two potential enhancement methods for the replica consistency by modifying two kinds of system configurations, still by somewhat sacrificing the read latency. While the study is mainly conducted on Cassandra, the conclusions are generalizable to other quorum systems such as Rayak and Voldemort, I'm sorry for the pronunciation, as they have similar architecture as Cassandra. Moving to the next slide. It is introduced in four types of session guarantee consistencies. First, catch the read and write process in Cassandra and analyze the causes of inconsistency. Methods to control the queue length and make the queue more stable. Describing experiment environment and workload setup. Studying the relationship between write queue length and the consistency degree under the different workloads, such as throughput number of clients, number of replicas, read or write ratio. Validation of effectiveness of consistency methods, both independently and collectively, and discuss their adverse effects. Compare related works and then conclude. Session guarantee consistency models. One of the well-known client-centric replica consistency models, session guarantee was first introduced in Terry et al. And further discussed and formalized in recent years. Session guarantee contains four types of consistency models: read your writes, monotonic reads, writes follow reads, and monotonic writes. So I'll just need a minute. So yeah, continuing to the table, we have different types of consistency models here. So read your writes. Read your writes in one session, if a read R follows a write W, the return version of R must be fresher than or equal to the version that W writes. Then the system satisfies read your writes consistency. Monotonic reads consistency. If in one session, if a read gets a data version V, then the versions that are subsequent reads get must be fresher than or equal to the version V. Then the system satisfies monotonic reads consistency. Writes follow reads consistency. In one session, assuming that a write W follows a read R and the version which R gets is V, W can be applied on the replicas whose data item version is fresher than or equal to V. Then the system satisfies writes follow reads consistency. Monotonic writes consistency. In one session, if a write updates a data item as version V, then the subsequent writes must be applied on replicas whose versions of this data item are fresher than or equal to V. Then the system satisfies monotonic writes consistency. Next slide. The scope of session guarantee. To analyze the internal cause, one should clarify the in a session represents that one and only one connection is established between the client and the cluster. The most important constraint is that a client can send a new request only after it has received a response of the previous request. Therefore, there is no chance that a cluster receives the latter request earlier than the previous one. The write queue and consistency. First, there are some terminologies and symbols in this. We are only concerned on participating nodes such as coordinator and non-coordinator nodes for a request. The value of data item A on the ith node is A of I. Read of A represents a read request for the data item A. Read of A, V represents the return value of the read request for A is V. Write of A, V represents modifying the value of A as V. Next slide. From here, my friend Vishnuvardhan Reddy Meda will take on the presentation and will continue to explain more about the literature review.
Well, thank you, Hitesh. Hi, everyone. This is Vishnuvardhan Reddy Meda. So, as was discussed in the previous slide, the write queue and consistency, we have defined some terminologies so that you can understand what the read and write operations in the sequence diagram are. So the sequence diagram is proposed for the process of read and write in the Cassandra database. Uh, as you can see in the sequence diagram, there's a read request that follows the write A2, and then the write request, write A3 comes in the session one. The coordinator and the coordinator N1 is responsible for one replica of item A. Before the client sends write A to request, the values of A in the all replicas are 1. So in this diagram, this also constitutes a WARS model, where we extend the WARS model to explain the consistency anomalies occur in the session one by splitting the read and write process into fine-grained steps. Apache Cassandra will send response to the client once the update is finished for the write replicas instead of all replicas. The updates of the rest replicas are executed asynchronously. The read operation can be divided into 6 steps, as you can see. The read digest, read propagate, digest response, propagate response, and return result. Uh, all these requests are from step 5 to step 10 in the sequence diagram. Also, Cassandra only requests for data from replicas that are considered as fastest nodes by the coordinator. So consistency metrics. This study does not sentence that whether system satisfies or violates a consistency model. Uh, Whereas it counts how many operations that violate a consistency model and then calculate the rate of consistency to indicate the consistency intensity. So we can see the consistency intensity here. It is defined as IC equal to 1 minus K by M, which means in an experiment of session guarantee model C, suppose the observer client sends the request M pairs. In the M request pairs, there are K pairs that violate the consistency model C. Then the consistency intensity is the IC equal to 1 minus K by M. That's how we get the consistency intensity. And the root cause of consistency anomalies. According to several scenarios of consistency anomalies, the major reason where the inconsistency occurs is that some write requests wait too long to be finished. So in a case where the write request can be finished in time before the read request comes, then the inconsistency can be avoided. Uh, so a corresponding structure for writing data in Cassandra is the write queue, which obeys the first in, first out strategy. So the Cassandra Apache follows the FIFO strategy to avoid the inconsistency here. The longer the write queue is, the higher the probability that the condition of read your writes anomaly could be met. Therefore, we can come to an opinion that length of the write queue can be a reasonable indicator for quantifying the degree of consistency. So this slide concludes that the major reason for the inconsistency in a database is the length of write queue. So this is a diagram for write queue as a real-time indicator of inconsistency. It is a sketch how to show the write queue length to quantify the consistency in the real time. We acquire the queue length by Java management extensions, abbreviated as a JMX in real time for each node. If the queue length of one node is exceptionally long, we can conclude that the consistency anomalies outbreak may happen. If the queue length becomes shorter, we can make a decision that the consistency becomes stronger. As we discussed the strategies of tackling inconsistency in the database, this is the third step, the experiment setup. In experiment setup, we initially design the experiments to verify whether the queue length can be a good indicator of the consistency, and then observe the relation between different workloads such as throughput, concurrent line number, and query distribution. Also, uh, read intensive, write intensive, and mixed workload are covered in these experiments. All these are different types of workload models. Uh, and then we verify the first two methods are effective for improving the consistency. The first two methods are read intensive and the write intensive. And also we analyze the adverse effects such as read and write latency in these experiments. Third, we verify the mixed workload method by analyzing jitters. Then combine all three methods to tune the consistency in the Cassandra database. Heavy workload setup. The workload is designed with three reasons. First reason is this workload stimulates the scenario of session guarantee well, which means it focuses on the feeling of one single session and use the observer client to observe the feeling of single session. Besides, it's impossible that one user use whole cluster. And the second reason is this workload is suitable for analysis. If all the clients are the observer clients, the workload is out of control, as it is not possible to control the write speed of the observer client. Heavy workload is more, and the third reason, heavy workload is more suitable for benchmarking NoSQL systems. Because many applications we see, they have heavily write workloads. So NoSQL systems may not be suitable for benchmarking this heavy workload. To cover all the types of workload, uh, the read and write ratios are changed. Continuation slide. When the experiment is done with heavy workload, we make some other settings to the hardware. First, we disable read repair mechanism in the Cassandra database. The read repair mechanism is which acts like an additional write for each read who reads the old data in an additional remedial mechanism to improve the consistency level. Second, the write latency may be very high with the heavy workload. Therefore, we set the operation timeout as 100 seconds to avoid the timeouts. So what we found under this workload is 1% to 50% operations violate the session guarantee consistency model. So here we can see the experiment setup. Uh, this table summarizes the experiment environments. Most of these experiments run on Amazon EC2 cluster C5. We can see the 5 clusters C1, C2, C3, C4, and C5. But when we consider the different network environment and CPU capacity, we use all of the 5 clusters. It is no doubt that YCSB21, which YCSB clients are the cloud serving benchmark for maintenance of computer programs. Also, there is a physical server Fujitsu Primergy R600S6. Also, the 40 cores, which means 4 by 10 cores of memory processor and 512 GB memory. We use the YCSB as a workload generator and performance reporter of the pressure client. In this experiment, the row key of the data is a long integer and the value of size of a column is 10 bytes. So here we have set the YCSB maximal executing time as 500 seconds. For each experiment, we run 5 rounds and discard the result of the first round to avoid the problem of the cold start. And then we calculate the average throughput as the final results because of official YSCB does not support Cassandra 2.0. We use the Cassandra 1.2.11 in this experiment. So YSCB client supports up to 6 nodes with YSCB 0.1.4 and the cluster size of the experiment is 5 nodes with Cassandra version 1.2.11. Continuation. So in the previous slide, we have shown the experimental setup where we can change the specification of virtual machines easily. For example, in the experiment, we have modified the CPU cores of the virtual machines from one core to four cores processor to observe the impact of hardware performances. So here both the Cassandra cluster and workload clients are running on the physical server to screen unknown factors. There is no virtual machines on the physical server. So what is the meaning? What it means when the cluster is in the cloud? Here we deploy the Cassandra cluster and workload clients on Amazon EC2 server. Amazon EC2 server is a way to provide the pay as you go visualization solution. Sorry, virtualization solution. And here it comes the queue length as an indicator of consistency. As we discussed, the uh, what are the main causes of inconsistency in the Apache Cassandra database. This diagram represents the relation between the change of queue length and number of read or writes consistency anomalies in the Apache Cassandra database. So this it shows the length of write queue on node 1 per 1 millisecond, and the occurrence time of consistency anomalies when the query distribution is uniform. So we can see the red line, which shows the changes of queue of one node in the cluster. The length of the queue fluctuates sometimes in the figure. As we can see, there is a fluctuation in the red line. After collecting the CPU utilization of Cassandra process and plotting the result, we can see when the CPU utilization changes, the length of the queue waves. So, sorry. As we can see, the relationship between the change of queue length, the bars in the bar graph means they show how many consistency anomalies occur in 10 seconds, so that we can find out the consistency anomalies that assemble when the length of queue is long. So the final result obeys their opinion about the relation of length of the queue and the consistency. Therefore, we can use the queue length to observe the consistency in real time. When the query distribution is uniform, we can observe any one node that is adequate. Improvement and stabilization of the consistency. So they have proposed two methods to improve the consistency. One is enhancing the service number capacity of nodes in the cluster by adding the write thread number, which means they have increased the number of write threads, and changing the quorum. Changing the write thread number, adding the write, they have added write thread numbers that can improve the consistency. However, a quantitative conclusion is not proposed. So an empirical quantitative conclusion is defined in the stabilization of consistency, and effectiveness of the consistency is measured. Continuation. Uh, the below experiment shows that the best thread numbers is twice of the CPU cores. So as we can see here, client number equal to 2k, which means the thread number is 2 times the CPU cores. Uh, this graph actually shows the changes of the queue length in real time on the cluster C2 when the concurrent client number is less than 2500. The service capacity of the node is enough. The node cannot handle so many requests when the client number is equal with 2500. When the thread number is equal the 2 times the core of number of CPU cores. For example, if it's a 4-core processor, it is which is a multiple of 2 by 2, the node can provide the maximal service capacity. So after changing the write thread numbers, we also analyze the adverse effects of changing write thread numbers for the consistency. So in this scatter plot, we can see there are a number of write threads on the x-axis and write latency and read latency with milliseconds on the y-axis. As one of the limited sources, the more threads doesn't mean the consistency is better. Imbalanced resource allocation leads to other modules lack of computing resources. That is why increasing the write thread number will bring some adverse effects. Continuation. Read and write read and write latency with different thread numbers and CPU specifications, uh, increasing the write thread number brings many read latencies while adding the write latency. There may be a read latency which increases substantially. To analyze why the read latency increases, so we collect the detailed information of CPU under each number of write threads. Then they have come to an opinion that it, the inconsistency is because of the write module, which Cassandra takes so many threads that the read module does not have enough threads. As a result, many thread switch events occur, and then the thereby they increase the read latency. So as we saw the read and write latency effects of changing the thread numbers in this slide. Uh, when the write latency increases the little long with the increment of the write thread number, however, the read latency increases substantially. To analyze why the read latency increases, we collect the detailed information CPU under each number of write threads by using dstat command on Ubuntu. Now the second method, changing the quorum. In this, we will investigate how different write and read consistency levels impact the consistency by experimenting first. And then we analyze the adverse effects of read or write consistency level. The experiment runs, so the experiment is set up again on the Amazon EC2 server with 5 clusters C1 to C5, and then 5 ICSB clients, which acts as pressure clients. And then they establish the 2,500 concurrent connections with the cluster. So here the replica number is changed from 2 to 4. So there are also adverse some effects of changing the quorum for analyzing the consistency. Uh, the main insight is that increasing read and write uh, sorry the main insight is that increasing read and write will decrease the throughput. The interesting phenomenon here about the quorum and throughput is when we keep the quorum size of the read write thread constant, the throughput differs. According to the experiments, we make a conclusion that increasing the read and write consistency level will decrease the throughput sharply, while we increase the write consistency. So this table represents the summary of first two methods of tuning consistency, which is the increasing write threads and increasing the read consistency level. So you can see the tuning methods on the left side and the adverse effects and best choice for the consistency on the right side of the table. Uh, here for increasing the write threads, the CPU is 2 times the actual cores, that is number of write threads are increased, and there is an increase in read latency, and there is a inconsistency in write latency. Also increasing the read consistency level, keeping R plus W read and write constant, the throughput is decreased here. So related works for this research article, they have compared, the team of Professor Xiangdong has compared related works with their working model. So many theorems such as consistency, availability, and network partitioning, abbreviated as CAP, and PACLET, indicated that developers have to make many trade-offs when they design distributed systems. So the CAP theorem, which pointed out that system has to give up one of the three features, they are the consistency, availability, and partitioning. So these are the three features that system has to give up in order to attain consistency. In our database, Apache Cassandra, which allows users to choose the column size to tune the consistency. And another theorem, Packlek, which pointed out if there is no network partitioning, users need to make trade-off between consistency and latency. Continuation. Uh, when we say the terminology of consistency, it means replica consistency model. That is the client-centric system. Uh, Consistency model is defined as the contract between processes and data store. So there are different kinds of consistency models that can be classified as data-centric and client-centric models. Uh, in data-centric models, the ordering of read and write operations are shared and replicated data is right. Uh, in case of client-centric consistency model, which defines that data should be from the client view. So this entire research paper of Xiang Dong Huang and his team focused on the client-centric model, which is also called as a session guarantees. So conclusions. From the results that presented in the research article, the conclusions are drawn that how these conclusions help developers and researchers to improve their works. So what it means that at first they have discussed the consistency anomalies, which are different for developers, and also there is no you which is different for developers and researchers to improve their works. So in developers point of view, the observation of queue length is easy to be implemented. Therefore, they can observe the current length of the queue to monitor the inconsistency in real time. When the workload of the application changes, developers can tune the consistency intensity to guarantee the user experiences by using proposed three methods, which are read intensive, write intensive, and mixed workload. So in a word, developers can configure the system better using the queue length, which can be implemented easily. Continuation. In researchers' point of view, how this research article helps the researchers to find more methods to improve the consistency. Uh, the researchers can analyze the system with queuing theory and design new consistency control methods according to queue lengths. But when queue length is long, one can cause complicated control methods that guarantee the consistency. Thank you. For any questions, you can contact us to the provided email in the description. Thank you so much.
Thank you on behalf of the Group 12.